Hi everyone, welcome to the thermochemistry unit of our course. I'd like you to pull out your notes packet, and I want to begin by just pointing out some definitions that you need to know for this unit. I'm not going to spend a lot of time on this because these definitions are printed for you, but I do want to highlight and make sure I draw your attention to them so you can look at these later. It says energy here. Energy is the capacity to do work or to produce heat. In chemistry, we're going to talk more about the production of heat or putting heat into a reaction. Also, one of the more important characteristics of energy is that it is conserved. So want to draw your attention to the law of conservation of energy. That states that energy cannot be created nor destroyed. So in this class, energy can be transferred from one thing to another, but we cannot create it out of thin air. It cannot be created or destroyed. Also, the energy of the universe is constant. So this is very important. Energy of the universe is constant. Also, the types of energy we're going to be looking at. Energy is classified as either potential energy or kinetic energy. Potential energy is due to the position of something. So if I were standing here holding a ball, just like this picture that's in your notes, let's say I'm a person right here, and I'm standing, I got my little stick figure here, and I'm holding this ball up in the air. Well, this ball is not moving if I'm holding it, but it does have potential energy. It has energy due to its position, where if I released it, it would move. Now, the kinetic energy of an object, that's due to its motion. So if I actually threw the ball or let it fall, as it's falling, it has motion. It has energy due to that motion. And that's described by the equation. Kinetic energy is 1/2 mv squared. Let's look further down at temperature. Now, temperature is a property. It reflects the random motion of those particles. So I want you to think about kinetic energy when you think about temperature. Temperature is proportional to the kinetic energy or the motion of those particles. So one thing I really want to stress is, in this class especially, all gases at a given temperature, they have the same kinetic energy. And I'm going to abbreviate that KE. So all gases at a certain temperature have the same kinetic energy because the temperature is proportional to something's kinetic energy, the motion of those particles. Now, heat, on the other hand, that involves the transfer of energy between two objects, and that occurs due to a temperature difference. And we're going to look at that later. The equation for heat equals mass times the specific heat times that change in temperature. So Q equals heat. And we're going to look at that on page 5 of your notes a little bit later. Now, the system, whenever we're talking about thermodynamics, defining our system is very important. So if we're talking about a cup of coffee, we'd be thinking about the coffee inside that cup if we were trying to describe its thermodynamic properties. So everything else would be the surroundings. So if we are talking about a cup of coffee, the coffee itself would be the system. The cup, the room we're in, everything else in the universe is the surroundings. Now, a reaction or whenever you produce heat in a reaction, it's said to be exothermic. That means energy is flowing out of your system. On the other hand, reactions that absorb energy from the surroundings is called endothermic. So energy gained by the surroundings must be equal to the energy lost by the system, because remember, the energy of the universe is constant. So let's move on to page 2 in your notes. And we're going to look at some potential, some diagrams that talk about heat and endothermic and exothermic. So let's call this our system here. So from the system's point of view, if heat is coming into that system, this is an endothermic reaction. So this tells you that your energy, this delta H, is your enthalpy. That is talking about the energy flow of that system. That is a positive number. So you see how delta H is greater than 0. That's endothermic. That tells you that your system is absorbing heat. On the other hand, whenever you have a system and heat is leaving that system, that enthalpy change, that delta H is negative. So that tells you an exothermic reaction is one that releases heat or energy. And this first one, endothermic, means it absorbs heat or energy. And in this course, we're primarily going to talk about that energy being in the form of heat. So let's look at the definition for thermodynamics, because that's what we're studying for this unit. It's the study of energy and all its conversions. And the law of the conservation of energy is called the first law of thermodynamics. It says the energy of the universe is constant. We put that twice in your notes because it's quite important. Also, the thermodynamic quantities like heat and enthalpy, those quantities consist of two parts, a number and a sign. So whether it's positive or negative indicates the direction of the flow of that energy from the system's point of view. Now the units that we use are joules. This is the SI unit for energy. That's what we're using here. And so let's now look at enthalpy changes. So here, our change in enthalpy is delta H. This is equal to the energy flow of that system. And what we're going to use here, this is a really important equation I want to draw your attention to. The energy change of any kind of reaction is equal to the energy of the products minus the energy or the enthalpy of those reactants. So let's look at energy flows of different chemical reactions. So let's look at the top of page 3 in your notes. We have here what are called potential energy diagrams. Now, when you're looking at these diagrams here on the next page, these show here on the left, we've got potential energy. So down here would be 0 and it increases. Here, 0, it increases. Now here, reaction pathway. This just means as time progresses, as that reaction goes, this is showing the passage of time in that reaction going. So here, let's look at this first diagram. This is an endothermic reaction. That means that the reaction is absorbing heat. So let's give an example. So I'm going to put an example here. A balanced equation we've used in class before is calcium bromide plus sodium nitrate. That yields calcium nitrate plus sodium bromide. Now here, if this is an endothermic reaction, that means we have to put heat in on the left-hand side of the equation. Means in order for this reaction to go, it has to absorb heat. So heat is a reactant. We treat it as a reactant. It's going in on that left-hand side. So let's look at this. our reactants. These are our reactants. They are at a lower energy than the energy of our products. So do you see how the energy, you started out at a lower energy, you ended up at a higher energy of your products. So the potential energy of the reactants is less than the potential energy of the products. So that reaction must absorb energy so that it can end up at a higher energy level. Let's look at our exothermic potential energy diagram. So an example I have for this reaction is, let's do iron. Let's do 4 irons plus 3 oxygens. So I'm going to do the combustion of iron to give us 2FeO3. Now, in order for this reaction to go, if I tell you it's exothermic, that means heat is a product. So this means that heat is given off as part of this reaction. So for an exothermic reaction, exothermic reactions releases heat. Endothermic absorbs heat. Exothermic releases heat. So let's look at the potential energy of the reactants. So these are the reactants. Do you see they are at a higher potential energy than our products down here? Our product, which is the iron oxide. Now here you see how the potential energy of the reactants is greater than the potential energy of the products. So therefore this reaction must release energy. That's why heat or energy has to be given off as a product. Now this that I want to draw your attention to, these little activated complexes, that's on both. Basically this is just kind of an energy bump. In order to go from reactants to products, you got to put in a little bit extra energy in order to make that go, and then the reaction then proceeds. So that's all you need to know about the activated complex right now. This is just an energy required in order to start that reaction. So make sure you're familiar with these potential energy diagrams. Now I want to turn your attention to these conversion factors for the units that we're going to use in thermochemistry. 1 calorie, and note this is calorie with a small c, is equal to 4.184 joules. This you have to memorize, these conversion factors. So memorize these conversion factors. Also, 1 big C calorie. Now this we call big C calories equals a food calorie. So when you buy your food and it lists the calories, this is the unit that it's using. 1 capital C calorie is equal to 1,000 small c calories. So make sure you know these conversions so that you can actually use those in dimensional analysis. Now here, all you have to do is just practice your unit conversions using dimensional analysis. And so I'm going to show you where I've actually solved these. So you can pause this so you can check your work and make sure that you have converted these correctly. You've got big C calories being converted to small c calories to joules. So make sure you're careful with your handwriting to make sure when you're writing these that you don't get confused and you don't confuse your teacher when they're trying to grade these as well. All right, let's now move on to the next page in our notes. Page 4. We're going to talk about calorimetry. Let's switch this out and use my nice, pretty colored. There we go. Let's use my colored copy. Now here it has a picture of a calorimeter. All this essentially is two coffee cups that are nestled inside one another, just so the reaction that's going on inside can be insulated from the surroundings. We've got a thermometer here. We've got an insulated cover that keeps the any of the outside air or anything from influencing. And then this is just a metal or plastic stir rod that you can use to go up and down to stir that reaction without disturbing your thermometer. So here, the calorimeter, you can do the reaction and look at any kind of temperature change to see if that temperature falls or increases. Now on the bottom of page 4 shows different specific heat capacities of elements, compounds that you're going to need to use in your homework. And so make sure you keep this handy. Now I want to draw your attention to this one right here, water. This you have to memorize, because any other of these specific heats that you'll be that you need to use to calculate in class, you'll be given those on a test, but you will not be given the one for water. So make note of that. So what is a specific heat? It is the energy required to increase, here we go, the energy required to increase the temperature of 1 gram of any substance by 1 degree Celsius. So the units on that is joules per gram times degrees C. So I want to make sure I write that here. So for water, you have to memorize the specific heat for water. We use the letter C for specific heat. It is 4.184 joules per gram times degrees C. That is the proper unit. And this is what you need to memorize. So using that, we're going to look at page 5 at the top, where we're going to actually do some calorimetry calculations. Now here at the top of page 5, it lists, we call this the mcat equation. So mcat equation. And this is what we're going to be using to calculate heats of different reactions. So heat is our Q. The mass of the object is given the constant is, or what we're using is M equals the mass of that object in grams. C is the specific heat of that substance. Remember, that's how much energy is required to increase 1 gram of that substance by 1 degree Celsius. And then this delta T, that's the Greek letter delta, meaning change in temperature, is that change in temperature is the final temperature minus the initial temperature. So all we have to do is, if we are asked to calculate the heat of a energy transfer or of a chemical reaction, we can use this mcat equation. All right, let's work a few of these MCAT type of problems. So for question number 1, it's asking how much heat is required to warm 122 grams of water by 23 degrees Celsius. Well, we say Q equals MC delta T. How much heat is required? Well, that's what it's asking us for. The mass is 122 grams of water. It doesn't give it to us, but we have to have memorized the specific heat of liquid water is 4.184 joules per gram times degrees Celsius. And it says how much heat is required to warm it by 23 degrees Celsius. Well, it doesn't tell us what our initial temperature or the final, but it does tell us how much it changed. So that delta T is 23 degrees Celsius. Now, is that temperature change a positive change or a negative change? Well, we know it is a positive change because it says it warmed the water. That means the initial temperature is smaller than the final. So if you warm the water, the final temperature is bigger. If this number's bigger, your change in temperature is positive. So all you have to do is put that in your calculator, and I will say, how many significant figures do you need to provide? Well, here I've got 3 sig figs, I got 3 sig figs, so my answer should also be in 3 significant figures. I get 1.17 times 10 to the 4th joules. Do you see how the grams canceled and the degrees Celsius canceled, leaving us joules? And I'm going to box my answer. Now, I'd like you to try working each of the next examples. I want you to try to work those. So pause the video, work those examples, and then I'm going to show my work so you can check and see how you did. All right, now hopefully you've paused and you've done calculations for 1, 2, 3, 4, and 5. I'm going to talk to you about number 6 separately in a moment because that one was a little different. So number 2, it gave you your mass. It gave you your initial temperature is 25 degrees Celsius. It tells you your final temperature of that ethanol is 78.8 degrees Celsius. It gives you the specific heat, and it asks you to say, calculate how much heat is required. So when you plug that into your MCAT equation, you end up getting a positive 4.52 times 10 to the 3rd joules. So making note here that all of these numbers you were given each had 3 sig figs, so therefore your final answer needs to have 3 significant figures as well. Now number 3, you were given a mass, you were given an initial temperature of 50.4 degrees Celsius, you were given a final temperature of 25 degrees Celsius. It tells you the heat, it gives you the Q is 114 joules. So it tells you the iron is cooled from T initial to T final. So then you've got to think, what is the sign on this Q? Well, if the temperature is being cooled, that means energy is leaving that iron. If you think of iron is your system. So if energy is leaving, then that tells you your Q is negative. So you need to put that in as a negative number. So you plug that into your MCAT equation so you can solve for the specific heat of the iron. And again, you have to check to make sure you have the proper number of significant figures. I've got 0.449 joules per gram times degrees Celsius. Let's look at number 4 and number 5. Well, number 4, it gives you a mass in grams. It gives you your final temperature. So it says a mass in grams at 65 degrees Celsius. It lost 9,750 joules. So that means it's a negative 9750 joules. What was its initial temperature? So you plug that into your MCAT to solve for your initial temperature. The initial temperature was 72 degrees Celsius. A quick check is double check your math to make sure your initial temperature should be greater than your final temperature of 65 degrees, and it is. So a quick mental check to make sure your answer makes sense. Now number 5, it gives you a sample of copper metal. It says it's cooled from, this is your initial temperature, and 33.1 degrees Celsius is your final temperature. It says it releases 126 kilojoules of heat, so that means it's negative. Q is negative 126 kilojoules. What's the mass of that copper? Well, you plug those into your MCAT equations and you do the math, being careful with your positive and negative signs because that's what can throw you off on these. And your final answer is 4,980 grams or 4.98 kilograms. Well, now let's look at question 6. Now, question 6 is a bit different. It gives you information for 2 different substances. So I'm going to put on a blank piece of paper here so we can work this together. So think about, let's say we have a hot piece of lead. So we heat up a piece of lead, and now we're dropping it into water that is cooler than that lead. Now remember back when earlier, a few moments ago, we said that the energy of the universe is constant. So if we drop that hot lead into cool water, the energy lost by that lead is going to be gained by that water. But the energy of the universe is constant. So that means the energy or the heat of the lead plus the heat of the water has to equal 0. So the lead will be a loss of energy. This will be a gain. Whenever you add those together, you're going to get a 0 net change of the energy in the universe. If you use this equation, you'll always get the sign on your answer correct because your temperature changes will take care of the signs in these mcat equations. So all we do is we're going to do an mcat equation for lead and an mcat equation for water. So lead, the Q for lead is just mass of the lead times C of the lead times the delta T for the lead. We're going to add to that, so let's put this in brackets because that's all one number. We're going to add to that the Q of the water. We can substitute our mcat equation for water in here. So the mass of the water times the specific heat of the water times that change in temperature for the water, that all equals 0. So now all I need to do is I need to write down what was given in the equation. So let's write down for lead. It gave us a mass of the lead is 200 grams. It gives us the specific heat of that lead is 0.127 joules per gram times degrees Celsius. It says it's at 170 degrees. Well, that's the initial temperature of that lead. So the initial temperature of the lead is 170 degrees Celsius. Now it switches and gives us information on the water. So I'm going to write a different list of variables for my water. It says the mass of that water is 100 grams. The water is initially at 40 degrees Celsius, so the T initial of the water is 40 degrees Celsius. Now, it doesn't give you the specific heat of the water, but you have to have memorized it's 4.184 joules per gram times degrees Celsius. Now it's asking you, what will their final temperature be? So the final temperature of the lead and the final temperature of the water, what are they? Well, the beautiful thing is when you drop the lead into the hot lead into the cold water, after time they're going to come to the same temperature. So these T finals are the same. So all you have to do is now plug these numbers into our equations and solve. So I end up getting the mass of the lead is 200 grams. The specific heat of the lead is 0.127. The temperature change for the lead is T final minus the initial temperature of the lead, which is 170 degrees. Now let's add to that the mcat equation for the water. The mass of our water is 100 grams. The specific heat of the water is 4.184. The temperature change of the water is the T final minus the T initial. Well, T final we're trying to find. T initial is 40 degrees Celsius. Now, when we add all that up, our final answer should be 0. So all you have to do at this point is a bit of algebra to solve for your final temperature. So I multiply by 200 by my 0.127, multiply that by TF. And then these two numbers, you multiply by that. So I end up getting, let's show you my work here. I get 25.4 T final minus 4318. So that's these two numbers times that. Now let's do 100 times 4.184. Well, that's 418.4 times T final minus 16,736 equals 0. So you combine the T finals and you combine the numbers to solve. T final is 47.4 degrees Celsius. Now one quick check. Your final temperature should be somewhere between the cold water that started and the hot lead. So if you get something that's not between those two numbers, you know you've probably made a mistake somewhere in your calculations. Now that I've shown you how to work each of these example problems in your notes, I want you to take some time tonight and rework, if you need to, those calorimetry problems in your homework on page 3 to make sure you get those correct for next class. I'm going to check all that homework.